Okay, so this is a quick kind of methodsy primer overview to give you an intuition of what empirical dynamic models are and what they we can use them to what kinds of biological questions we can use them to answer. And to little disentangle empirical dynamic models, what those are is what this is all about is basically getting the rules of change in biological systems, so their dynamics, um, from the directly from the time series that we have, okay, empirically. Okay, so a little bit of motivation for this on the practical side. What I think is really exciting for this is recently we've had a tremendous number of tools that allow us to find patterns in data very easily. This is splines as well as things like machine learning, which is localized linear models, things like that. Um, but what's kind of missing is kind of a really easy to use tool. I think empirical dynamic models are a great candidate for this, for one of these tools, where we can just look at a data set at a time series and ask, are there consistent patterns in its dynamics? Okay, so not just patterns in kind of what systems look like, but patterns in how they change. Okay, and kind of related to that is how do we make accurate forecasts in ecosystems and in biological systems and management questions. A little bit closer to home for us, where we're interested in understanding mechanisms. I've been raised by this on this idea, and I really love it. That we can find mechanistic models that and the mechanisms that underpin biological dynamics. But to do that, what we need to do is to guess the right interacting species and environmental variables that are important in a system, and then guess the right functional forms for how all these things interact. Okay, and so this takes a lot of biological knowledge. This takes a lot of data, um, both directly and indirectly, and this often takes some time series as well, and some very careful statistics of how we integrate um, the dynamics and our data. Okay, and so kind of an immediate question is how can we guess better? Okay, get to the right answer more quickly, whether if we have some indication of what the functional forms are, or what the important variables are. Uh, a lot of the time, we just want to know also coarse properties of the system. Okay, things like how much stochasticity is there, are the dynamics deterministic? Is there any consistent change to explain? Also, things like how many lags in the dynamics are important, right? The length of the deterministic memory of the system. Um, is it stable? Do dynamics differ from location to location? Okay, and these are aggregate properties that we don't necessarily need to know all the mechanisms for. And in fact, when we force some time series data to fit a parameterized mechanistic model, we might be losing important aspects of the data. And then finally, a lot of the time, we just don't have enough information. We don't know enough about the system to make a guess of what the dynamics are. Okay, so a lot of the time, we're dealing with ecosystems like this, where we have many, many species and many, many possible interaction types. Okay, so what that means is that there's a huge set of possible simple models that will do a very good job of explaining nearly all of the dynamics. But which set of processes and species are important, we don't know a priori. You can also look at this as, there's many species and interaction types, so there's, maybe the right model is something really, really huge, okay? I don't think that's right because if that's true, we'll never be able to parameterize that model. Okay, we should think of ecosystems and complex systems as, any particular one. There's going to be a collection of processes a few processes that are going to be important. But what those processes will be will vary from system to system. So that's kind of the view I have. And then kind of the other terrible news here is that usually we have relatively little data in ecosystems. And when we're talking about dynamics, we usually only have data on a few species that we deem to be important for some reason. Okay, so the way we're going to go about this, analyzing a time series from an ecosystem is that we're going to assume that there's some kind of attractor. Okay, an attractor is just an area of state space in our ecosystem, an area in the coordinates where the system, tends to approach and it tends to stay there once it gets there. Okay. The core tenet of why we assume that most ecosystems have an attractor, is that species densities are not constant. Okay. Even if your attractor is deterministically is a steady state, okay, constant carrying capacity, for instance, uh, as long as we have noise, demographic and environmental stochasticity, it's going to keep pushing us away from the attractor, and the system is always going to be trying to come back, and maybe it'll come back for a bit, and then it'll get pushed away. Okay, so there is even when the attractor, in the deterministic system will give you no information on the dynamics of the system. When we have noise pushing the system around and exploring state space, we can learn some of the rules of the dynamics. Okay. Um, and so once we, kind of have this idea of attractors, as a way to look at the patterns in ecosystem change. Now we can think about what those attractors look like. So specifically their, for instance, dimension. Okay, one example is kind of logistic growth. It's one-dimensional because there's only one species. Another example is predator-prey cycles. Now we have two species and the attractor is a circle. Okay, with 3 dimensions, we have things like the food chain model and the teacup attractor, and of course, the famous Lorentz butterfly attractor um, when we're looking at atmospheric dynamics. And then, of course, these things could be quite big. Okay, here's a simulation of a 1,000-species Lotka-Volterra system, and here's what a time series of one of those species looks like. Okay, so kind of our saving grace here, or our approach here is to use time delay embedding. Okay, so Flores Hawkins had this beautiful theorem on this, and you can read it on your time. But what it boils down to is that if we have a system of n species, or maybe environmental variables are also important, we can reconstruct the dynamics of any one of those species exactly just from the time series of that species. Okay, we can account for all the dynamics in the system as they influence that species using just one time series. Okay, one slice of the system. And we'll need the length of that time series that will need to be is less than 2n. Okay, if the time series are deterministic. In practice, with noise, we'll need more data. But the upshot is that with a pretty short time series, we should be able to reconstruct the dynamics of a system exactly. Here's a little bit of a visual intuition for what time delay embedding is. Okay, we have this butterfly attractor in the Lorentz system. It's in 3 dimensions. There's 3 variables here. If we only have data, a time series of x, okay, so that's what it looks like. We can plot x, and then we can also plot x shifted to the right a little bit. Okay, so this second row is exactly the first row, shifted to the right a little bit, and x, so that's x at t minus tau, and x at t minus 2 tau. Okay, so that's that same time series shifted to the right again. Okay, and now if we plot x of t versus x of t minus tau versus x of t minus 2 tau, we get this thing. Okay, so this is a kind of a shadow of that original attractor that preserves important properties like the topology and Lyapunov exponents, like stability questions, things like that. Okay, so that is what that looks like. There's also a mathematical intuition for where we're basically substituting gradually. We have some observed and unobserved variables, and gradually we're substituting our unobserved variables with time lags of our observed variables. Okay, and you can take your time to go through that, and this is a little bit more of a mathematical precision on what our reconstructed map is. Okay. And now to give you a little bit of a simple example of maybe a little bit more practically of what we're actually doing, what these models look like. So for example, if we have an attractor again with dimension 3, and we have a series of training time series n, just a set of numbers, we can give every observation in our time series a set of coordinates. So what it is now versus abundance last year and 2 years ago. So that's a set of 3 coordinates. Now we can plot everything in 3D space, and if we connect points, adjacent points in time, we'll get this set of blue lines here. And now if we have a new observation for which we want to predict where the system will go next year, we have a very simple algorithm. take where the system is now, that point in that 3D space, find E+1, so the 4 data points in the training set that are closest to that part of time delay embedding space. Okay, in this case, that's these 4 circles. Then look at where those 4 circles go in the next time step and take the average of them. That is our best prediction of NFT+1. That's the entire model. Okay, what does this model look like visually? Okay, well, here's the true dynamics here are this logistic map. Okay, so it's just a quadratic thing, and maybe our time point, our data points in our training set fall on these values. Okay, so if we want to predict for a new data point and star of t, and we're at point 1, our best prediction of that is the average of these 2 points. If we want to predict things for this point, our best prediction is the average of these 2 data points. Okay, similarly, if we have a 2-dimensional system, now we have to think about, both 2 lags of population abundance. Okay, so we have 2 coordinates now. This is embedding dimension of 2. And now we look at 2 plus 1 adjacent points. Okay, if we want to predict if the system now is at this abundance level and it was at 15 a year ago was the abundance. Now, if we want to predict abundance at t plus 1, the color here, we're just going to find the 3 points closest to that and take their average. Okay, and similarly for here. Okay. Now, what we're effectively doing, this approach is called simplex. Okay, it's the very simplest thing you can do, is we're basically approximating these functions with a step function. Okay, the resolution of that step function is how many data points we have. Okay, so it might be really coarse like this here, or it might be a really fine scale, but it's always a step function. Okay, it's a step function if we have a 1-dimensional system. In 2 dimensions, it's going to be like these very pixelated view of the same image. Okay, but the importance is that it's not differentiable. Okay, to make things a little bit better, one improvement we can do is an algorithm called SMAP. Okay, now we're going to be doing local linear regression. Okay, so for that same example point I showed, instead of just taking the average of these 2 points, we're going to take the slope of NFT plus 1 with respect to NFT. Okay, so we're going to do a linear approximation of NFT plus 1. And we're going to use all the points to make this approximation, but we're going to weight points that are farther away in terms of NFT less. Okay, so we're going to use, for instance, this kind of kernel where the weight of a data point in this, so how much a data point, any of these data points contribute to that to the slope of that linear regression is going to decline exponentially the farther away it is in phase space, or in this case with NFT. Okay, so our weights decline exponentially with the rate theta. Okay, and then when we do that, we get a much closer approximation of the underlying dynamics with a small amount of data. The key thing here is now we get a function that is continuous, which means we can do derivatives. Okay, if we have multiple time series that we're plugging into this free construction, it means our slopes are species, and potentially species environment interactions. We get the actual Jacobian of the system at any given point in state space. Okay, and also I should say this kind of theta, which governs weights, that is, that length scale is kind of a test that we can use to ask whether we have nonlinear dynamics in the system. Okay, if theta is 0, then all the points for any NFT, all the points get equal weight, which means all the points fall exactly on a line. Okay, so there's no nonlinearity at all. Okay, and kind of as a side note, there's also one more kind of level of intricacy that we can do for predictions here, which is Gaussian processes. We still have this idea of theta and kind of locally weighing points nearby to where you're making the prediction more, but also things don't necessarily have to be linear. Okay, so Gaussian processes let us do nonlinear functions. They also better capture uncertainty, and we can also, with this approach, very easily make spatially explicit and hierarchical models. Okay, and you find those in the R package GPDM. Here's a couple of practical FAQ things that you might have just for reference. Um, Now, one question is, you have time lags here. Is EDM and time delay embedding just an autoregressive models? Uh, and the answer is yes, in the degenerate case where theta is 0. Okay, so in the simplest case, EDM is autoregressive models. But if there's any kind of nonlinearity in the system and how the variables interact, EDM is going to do better. Okay, and so kind of for example, and so there's to dive a little bit deeper into this briefly, if we have a logistic map, and if you've seen cobwebbing, this will make sense. If you have a logistic map and you have this 2-cycle, autoregressive models can do okay because you just fit 2 time lags now, and you fit kind of a slope for every time lag, and then it works fine. So autoregressive models can account for a little bit of nonlinearity, but once you have something like chaos where you're really sampling the entire curve, the entire nonlinear curve in this quadratic map, now you need an infinite number of lags in an autoregressive model to account for this. Okay, so in summary, EDM is going to outperform autoregressive models whenever the system samples a lot of different sections of these nonlinear responses. Okay, so in particular, that's going to happen whenever we have chaos, or whenever we have, such as on the left here, this is a fully deterministic simulation, or when maybe the deterministic dynamics of the system is just again a steady state, but we have environmental disturbances pushing the system around. Okay, so the deterministic dynamics are here. I add some noise, and in the simulation they become this, and we see that EDM still outperforms autoregressive models by a lot. A little bit of one more side note comparing EDM to symbolic regression. Symbolic regression can do very well, and kind of with the premise of giving us the actual equations without having to guess them. And it performs well in low-dimensional systems where and there you can have kind of complex interactions and check all many possible interaction types. Or we can do SIMD in high-dimensional systems, but then we need a very limited set of interactions, and maybe we need kind of equations where everything is additive, basically. And maybe a limited set of which variables interact with which. Okay, so you can do complex interactions in simple systems or simple interactions in high-dimensional systems. EDM can do both. Okay, with EDM, we also don't assume that dynamics follow a single function at all times. Okay, but we can allow for that. And also, when we're using Gaussian processes to model EDMs, these approaches also do a really good job of capturing how noise interacts with nonlinear deterministic dynamics in the system. Okay, and so much so that even if you get the right model, or if you use the right model, EDM will still outperform the right model when you have stochasticity in questions like forecasting. And so check out the paper if you're interested. And with both of them, I think kind of the limitation is that these are partly black box models. So you are losing something a little bit, which is that biologically interpreting them can be a little bit tricky. Okay, especially if you just have one time series. If you have multiple time series, that can help you parse things apart. Okay, one more question that comes up a lot is like, you're assuming that there's a train attractor, but we have environmental change. What happens if we have non-stationarity? Okay, and the answer is we can account for non-stationarity if we include the aspect of environment that's changing, or time as predictors. So we have kind of multivariate prediction. You can fit differences in the time series, difference time series. Doesn't always work so well. And there's also a couple of other approaches. Also, if this question of what if our time series isn't long enough? So typically we need, kind of in my experience, you often need at least 30 years of data if you're working with fish, mammals, things like that. And usually you kind of do well when you have 50 or 60. Okay, so what if you have 30 or like 25? Well, one thing you can do is use time series, maybe have them from multiple locations. And then you can assume that all the time series, all the locations have an identical attractor. So there's like, using space for time substitution. If you're using Gaussian processes in EDMs, you don't have to do that. You can allow this for the model to include differences in the dynamics and the attractor in different locations in hierarchical processes. You can also plug in multiple variables if you have more than one time series in the system. That can sometimes help. And there's also a fairly complicated thing called multi-view embedding. Sometimes it helps, but I won't get into that here. Why are we doing all this? What have we actually learned when we've been using this, black box approach? Well, one thing we've learned a lot is ecological interactions. I mentioned with SMAP, when we have multiple time series that we're kind of plugging in and using to predict at the same time, now we can get Jacobians, which is kind of linear estimates of how each species affects every other species, okay? So we can get estimates of species interactions and how they change over time as the system moves through the state space. Another really important implication is convergent cross-mapping, which lets us kind of detect causal interactions in an ecosystem and again, how they change over time. So a little bit more detail on that. Suppose our kind of full model of the ecosystem, the true dynamics of the ecosystem have 3 important species and they follow this attractor, but we don't know what that model is or anything about the system. We just have, for instance, a time series of herring, okay? And as I've shown you with the time delay embedding, we can plot herring now versus how many herring last year versus how many herring 2 years ago and reconstruct the original attractor with just the time series of herring. We can do the same thing with if we also have just the time series of cod. And then we can ask, how are these manifolds related? Okay, in particular, can we use the map of the herring dynamics to predict changes in cod? Okay, and specifically, as we put more time points in it, as we have a better map of herring, are we able to predict cod better? Okay, if they're really sharing the same attractor, they should be very closely related. If and this lets us kind of tease apart the role of how related and causally related two variables are versus if they're just correlated in time, or if sometimes they're not correlated, but they are causally related. Okay, so this lets us detect interactions in complex systems, and in particular, what's really exciting is that we can kind of scan, do windows in time, and look at how interactions, for instance, in plankton food webs here, in a bunch of different lakes, how interactions change over time. And finally, we can learn a lot about kind of fundamental ecological processes. Again, those core system properties. Fundamentally, just ask, do these black box models do a good job of predicting things? If they don't, it means your time series is mostly stochastic. There's not much deterministic pattern there. Okay, you can also fit a mechanistic model and then take the residuals of that model and see, is there any consistent patterns in the dynamics left over? I've mentioned tests for nonlinearity. With SMAP, we can also calculate local and global Lyapunov exponents. Okay, and ask, is there chaos in ecosystems? And importantly, back in 2007, people fit a theta logistic model, which is one-dimensional, and found that chaos almost never happens. More recently, Rogers and Munch took the same set of time series, a little bit shortened, so trimmed, so we get kind of longer time series. But then we fit EDM models with dimensionality up to 6, okay, which is saying that ecosystems aren't necessarily one-dimensional. And when we do that, we find chaos in about 30% of species, okay, more so in short-lived species. Okay, so so we've learned that chaos is not necessarily rare in nature. And what I've been using EDMs for is looking at how much do the rules of ecological interactions, so those deterministic dynamics, how much do they vary from place to place in an ecosystem? Okay. And so here is 4 species in one location. The black are the data. The blue are the predictions of EDM, the deterministic model. So you see that there's consistent deterministic dynamics. But as we go to different locations for every species, the dynamics change, and EDM captures that. And so there's also a set of ecosystem management questions we can ask. including robust forecasts, things like optimal control. Here's some papers on that. And also we can interpolate dynamics across conditions and generate things like early warning signals. And so just kind of as a last slide to prime you on that, here's an experimental system where we have two consumers that interact with each other and use the same resource. On this plot here, so they live in a chemostat. So on the x-axis is different experimental conditions. On the y-axis is abundances. And what I want to highlight here is that there's data on the system only at 3 x-axis values, okay? This one where we see cycles in the data, and this one where we see chaos in the data, and in this one where we see things are at steady state. And just by fitting EDM to those 3 experimental runs under those 3 flow rates, we get all the other data points, all the other points on this graph, okay? And so now we see the full bifurcation diagram here, period doubling, the emergence of chaos, period halving, the kind of emergence of an equilibrium at high flow rates, okay? And so this is something, so here, this is how it works. This leads, so in some questions that you can answer with EDM. And here's the software I use in R to do this. And if you're interested in learning more about this and in basically applying it to a project, I think it'll be pretty quick to try. And I'd be happy to give you guidance and talk about it more. Thank you.